Hello students, hope all are doing good. Today we are going to learn about the real number of class 10. So in this video I have taken class 10 chapter, that is first chapter, real number. So before going to the topic, I wanted to tell you that already I have made a video regarding the real numbers. So what is real number? Okay, and what is the definition, example in that, what are the types we have, like rational number we have, irrational number we have, in that what are the types we have. So everything already I made a video of that. Please go to that video, watch that twice or thrice. You have to understand the definition of each and everything. So there you will learn definitions of natural number, whole number, composite number, prime number, integer, even integer, odd integer, then real number, rational number, irrational number, all the definition explained in detail. So that link I will give in the description. Please go to that video and watch it twice or thrice. You will understand it very easily. Now directly I will go to Euclid's division lemma, that is the second topic of this chapter, real number. So first topic is definitions of all those different types of numbers, that already I made a video of that in detail. Please go to that. So now let's move directly into the topic, that is Euclid's division lemma. So what is Euclid's division lemma? We know that division is nothing but subtracting, repeated subtraction, right? So what is lemma? What is the meaning of lemma? We'll see now. So lemma is nothing but it is already a proved statement. So means somebody is already proved that. Okay, so it is a statement that is already proved. That statement we will use to prove the another statement. Okay, so lemma is nothing but it is already a proved condition, okay, or proved statement. Okay, by using that proved statement, then we will use it for another problem to prove that. Okay, now then what Euclid's division lemma states? See, it states that any positive integer can be divided by another positive integer in such a way that it leaves a remainder which is smaller than the positive integer. What is the meaning of that? Take any integer, for example take 5. Okay, this 5 can divide another integer 10, okay, and it leaves a remainder, take 11 here. So it divides, these 5 and 11 are the two integer, okay, two positive integer. Now try to divide this one. So 5 2s are 10, remainder is 1. See, always in Euclid's division lemma, okay, the remainder will always be smaller than the positive integer which we consider. Okay, that is the statement of Euclid's division lemma. Means any positive integer can be divided by another positive integer, that is 5, in such a way that it leaves a remainder which is smaller than the any of the positive integer. Okay, and this Euclid's division lemma is also called as long division process. Clear? Now we'll see what is that condition in mathematically, how we are going to write this lemma or statement, we will see now. Those who are making notes out of my video, please watch the video of the definitions of all the number system. Make a note of that, then you copy this topic. I am repeating one more time, those who are making notes out of my video, please watch the previous video of number system and make a note of it in your classwork, and then continue this Euclid division lemma. So mathematically, how we will write this statement? The statement is nothing but if a and b are the any two positive integer, to satisfy this condition there exist another two integer, that is q and r, okay, to satisfy the statement, that is a equals b into q plus r. So what is a here? A here is dividend and b is divisor, q is quotient, r is remainder. So this is the statement. So here a and b are any positive integer. To satisfy this statement, there exist another two integer, that is unique integer. We call them as q and r. Here a is nothing but dividend, b is nothing but divisor, q is nothing but quotient, r is nothing but remainder, where r is always greater than or equal to 0 and less than b value. B value is nothing but the divisor. Okay. Now we'll solve one of the example, then you will understand what is the exact meaning of that. Consider example problem, that is, show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Here we have to prove 2q and 2q plus 1 will exist in even form and also odd form. So how to prove this one? We have to use Euclid's division lemma method. Okay. So now we know that according to Euclid's division lemma, we have a statement, that is a equals b into q plus r, where r is greater than or equal to 0 and less than equals to b. So now according to this equation, write the given equation, that is a equals 2q plus 1. Here b is 2 and r is 1. So there exist, see, r is write r as it is. Okay. Consider b as 2. So now if b is 2, okay, then there is only two possible remainder. Okay, either 0 or 1, right? So it either 2 should give 0 as a remainder or 1 as a remainder. So the possible remainder for r is only, see, this r is greater than or equal to 0 and less than 2, means what? Either it should be 0 or 1. So the possible remainder zero and 1. So when r equals 0, then the statement will be the positive even integer, right? So when r equals 1, what will happen? A equals 2q plus 1. See, this is odd integer and this is even integer. So any positive integer, it can be exist in the form of 2q and also 2q plus 1. If it is in 2q form, it is a even positive integer. If it is in 2q plus 1 form, it is in odd integer form. Here you write even integer and odd integer. Now consider the second problem, second example. Second example is show that any positive odd integer, remember odd integer, it is of the form 6q plus 1, 6q plus 3, 6q plus 5. We have to prove that odd integer only exists in the form of either of these three. But it may be 6q plus 7 also, 9 also, then 11, 13, it will go on. But here what in the question, whatever they asked, you just prove that. So consider, according to the question, we can write it as b equals 6, right? So according to Euclid's division lemma, we have a statement a equals bq plus r. So if you consider b value here r, where r is greater than or equal to 0 and less than or equal to, less than 6. Here b is nothing but 6. This is 6. Don't get confused. This is 6. So what are the possible value of possible remainder? The possible remainder of r is, so you should not it should not equal to 6, it should be less than 6, or it may be equal to 0 also. So 0 you can consider because the equation itself satisfies r is greater than or equal to 0. So 0 is one possible remainder, then 1, 2, 3, 4, 5. Why you should not consider 6? R should be less than 6, not equal to 6. So these are the possible remainder. Now apply this remainder in the given equation. What will happen? You check it out. So when r is 0, what will be the equation? A equals, in this equation you have to substitute. A equals 6q plus r is nothing but 0, you will get 6q. So when r equals 1, a value will become 6q plus 1. When r equals 2, a will become 6q plus 2. When r equals 3, 6q plus 3. R equals 4, a equals 6q plus 4. When r equals 5, a equals 6q plus 5. So here this 2 and 4 does not exist as a odd integer. So except this and this is even odd integer. So only when r equals 0, r equals 1, r equals 3 and r equals 5, the given statement exists in the form 6q plus 1, 6q plus 3 and 6q plus 5. You no need to prove that, you just think if it is odd integer, only when the number is odd that equation will exist. Clear? So the time a will never be equal to 6q plus 2 and 6q plus 4. If it is not equal, it doesn't exist. Clear? Now let's consider another example. Next example is, show that square of any positive odd integer is of the form 4q plus 1 for some integer q. What is the meaning of that? See, consider any positive integer, okay, q. When you do square to that positive integer, even after squaring it will exist. That we have to prove. For that, consider according to Euclid's division lemma, we have a statement that is A equals BQ plus R, where R is greater than or equal to 0 and less than B. Okay, now consider any positive integer, it's up to you. Now I will consider 2m plus 1 be any positive integer, any positive odd integer. Now by considering this, I have to do square to that, then I have to prove it will exist or not. Now consider this as a 2m plus 1. Now square on both the side. What will happen? A square equals 2m plus 1 whole square. Now it is in the formula a plus b whole square, right? So expand. It will become 4m square plus 4m plus 1. Now from this take 4 as common, m square plus m plus 1. Now consider m square plus m as q plus 1, where q equals m square plus m. So even after squaring that positive odd integer, it will exist in odd form only. Okay, that we have to prove here. Now consider next example. if they ask this type of problem like squaring any positive odd integer or any even integer, if it is any positive even integer, we will consider 2m only. Okay, directly you can consider 2m and square on both the side, then you can prove it. Clear? Or you can consider 2m plus 2 because that is even positive integer, no, like that. Here they asked odd, so I consider 2m plus 1. You may have doubt here why I consider 2m plus 1, right? Because it is a first odd integer we had. Next odd integer 2m plus 3 also you can consider, nothing wrong in that. Now come to next example. Here we have to assume any positive even integer. Okay, any positive integer, then we have to prove it exists in the form 9m, 9m plus 1 and 9m plus 8. So I hope you are understanding the problem. We have to take any positive integer, then we have to cube it. Okay, after cubing it, we have to show that positive integer exists in the form 9m, 9m plus 1, then 9m plus 8. For that, consider we have to prove 3, no? So for that I will consider 3 different forms, that is 3q, 3q plus 1 and 3q plus 2 are the forms. Forms of positive integer. Now we have to take 3q and we have to prove it exists in the form of 9m. How to prove it? Consider a equals 3q. We know that what they asked in the question, cube of any positive integer. Now cube on both the side. If it is SBS, square on both the side. If it is CBS, it is cube on both the side. So a cube equals 3q whole cube. Now split this cube, 3 cube into q cube. 3 3s are 9, 9 3s are 27, 27 q cube. See, now this 27 you can write it as 9 3s are 27, right? Cube, where here m equals 3 q cube. See, first one 3q exists in the form 9m. Clear? In the same way we have to consider 3q plus 1, cube it and show it exists in the form of 9m plus 1. Then consider 3q plus 2, then show it exists in the form of 9m plus 8. Now consider the second one, a equals 3q plus 1. Here also cube on both the side. Now a cube equals 3q plus 1 whole cube. So it is exist in the form of a plus b whole cube, right? Now expand this according to the equation. What is the formula of this? A cube plus 3 a square b plus 3 ab square plus b cube. Now according to the standard formula, expand this one. What you will get? 3q whole cube plus 3 into a is nothing but 3q, b is nothing but 1, a square you have to do, then 3 into a is nothing but 3q, b is nothing but 1 plus b cube is nothing but 1 cube. Now split this cube, 3 3s are 9, 9 3s are 27 q cube I can write. Here 3 3s are 9, then 9 into 3 27, 27 q square plus here 3 3s are 9 q plus 1. Now here you can take 9 as common. So 9 3s are 27, again 9 3s are 27, 9 1s are 9 plus 1. See this here, this whole value will act as m. So where m equals 3q cube plus 3q square plus q. So this exists in the form of 9m plus 1. In the same way we have to consider the next one and we have to prove it exists in the form of 9m plus 8. Please make a note of it. You pause the video, make a note of it and continue. Now consider a equals 3 cube plus 2. A equals 3 cube plus 2. We have to prove it exists in the form of 9m plus 8. For that again cube on both the side. So when you cube it on both the side, what will happen? Again it will come in the form of a plus b whole cube. Please expand it according to that. So 3q whole cube plus 3 into 3q square plus b is nothing but 2 plus 3 into a is nothing but cube, b square is nothing but 2 square plus b cube means 2 cube. So what will happen? 3 3 is a 9, 9 3 is a 27q plus here 3 3 is a 9, 3 3 is a 9, 9 2 is a 18, 18 3 is a 54 q square you will get. Here 3 3 is a 9, then here 2 2 is a 4. So 9 4 is a 36 q you will get plus 2 cube is nothing but 2 2 is a 4, 4 2 is a 8. Now take 9 common in this. If you take 9 as common, 9 3 is a 27, your cube will be there, plus 9 6 are 54, then q square plus 9 4s are 36 q plus 8. See where m equals, this also existed in the form of 9m plus 8, where m equals 3q cube plus 6q square plus 4q. I hope you understood this problem. We'll see few more problem in exercise. Now let's move on to the next topic, that is Euclid's division algorithm. I hope you understood this. They will give see this is the already proved statement. Okay, so we have to assume any one of the condition and we have to use this one to prove the another statement. This is what Euclid's division lemma. Till now what we did is already they given one proved statement. Okay, we have to use that proved statement to prove another problem. Clear? So here already proved statement is nothing but Euclid's division lemma. By using that we will prove all these number will exist in even form and odd form. Now let's see Euclid's division algorithm. Next topic is Euclid's division algorithm. So here what we will do, why it is important we will see now. See, first you need to learn what is algorithm. Algorithm is nothing but it is a series of well defined steps. See, there will be continuous steps, okay, but it is already defined how you have to consider, how you have to prove. Okay, all the steps is already explained before itself. Then it will give you a procedure. Okay, there are some rules. Procedure is nothing but how to solve it, okay, by using well defined steps to solve a problem. We will see now. Okay, so Euclid's division algorithm, that is very easy in this chapter. So algorithm is nothing but, you just remember, it is a series. Series means continuous well defined step. It will give a procedure rule to solve any type of problem. Okay, so where we will use this one? See, this Euclid's division algorithm we will use in finding HCF of any two largest positive integer. Clear? If it is 2 and 4, it is very easy to calculate, right? What if they given in 1000 and 2000, 10,000, lakh? it is very difficult, right? So at that time we will use this Euclid's division algorithm to find out the HCF of two largest or greatest positive integer. Okay, now we'll solve few examples, you will understand it easily. First example is use Euclid's division algorithm to find HCF of 870 and 225. See here these two are very largest number, so how to find the LCF of this we'll see now. Now consider 870 and 225. So here which is the largest one? 870, right? So 870 is larger than or greater than 225. So consider this as A and consider this as B. Now we have to prove the statement, that is B into Q plus R, right? Consider 870 equals B is nothing but 225. So when you divide this 870 by 225, how much you will get? Check once. I think 225 into 4 you will get. If it is 4, it will become more, so it will become 900. So consider 225 3s. So what will happen? 3 5s 15, then 1 3 2s 6 7, then 3 2s 6. So now find the difference of this. 10 minus, take 1 borrow from 7, it will become 10. 10 minus 5 is 5, then this is 6, again take 1 borrow, it will become 16. 16 minus 7 is 3 9, then this is 7. Now 7 minus 6 is 1. So 225 into 3, this is quotient, no? And what is the remainder? Plus 195. This is how you have to consider the equation. You have to divide and check it out. Now consider this as A and this as B. Now consider 225 equals 195. You can solve only one time, you can divide only one time this one. 195 into 1 and the remainder will be 30. So now consider this as A and this as B. 195 equals 30 into 6. It will become 180. So the remainder will be 15. So now consider this as A and this as B. So 30 equals 15 into 2 and then remainder will be 0, isn't it? So until you get 0, you keep dividing this number. Okay, this is what Euclid's division algorithm. See, these are all the well defined steps to find out the HCF of that. So in which step you will get R equals 0, no? So that is the HCF of the given number. Clear? So in this step I got R equals 0. So you should not consider this 30 as a HCF. You should consider 15A as a HCF. So HCF of 870 and 225 is 15. Now consider another example. So the next problem is use HCF of 176 and 38,220. So consider the greater number as A and the lesser number as B. Now follow the same step and calculate. You will get 4 as a HCF of 176 and 38,220. You try this one. We will go to the next one, which is having 3 HCF number. Now consider the next example, that is find HCF of these 3 number. So in these 3, which one is larger? 324 is greater than 252 and greater than 180, right? Now first consider these 2 number and calculate the HCF. So consider this as A and this as B. So only once you can consider. So what is the remainder? remainder will be 72. Now consider this as A, 252 as A and 72 as B. So you will get 72 into 3. You do division and find out, okay. Find out the Q and R. You check it out once. 72 into 3 is nothing but 3 2s are 6, 3 7s are 21, right? So 3s are you will get, and remainder also. You please do division on your rough work and calculate it. So 72 into 3 and remainder will be 36. Now consider 72 as A and 36 as B. 36 into 2s are you will get 72, remainder you will get is 0. Clear? So HCF of 324 and 252 is 36. Now how to find out the HCF of this one? Now consider this as B and consider that as A. So 180 as A and 36 as B. So if you multiply 36 into 5, you will get directly 0. So 36 is itself a HCF of all the three number. Sometime you will get another number, you have to follow these steps, then you will get 0. So at that time you have to multiply it. Clear? So for all the three, HCF of all the three number, HCF of 324, 252 and 180 is 36. First you should consider two greatest number, calculate the HCF. Then that number you have to consider as B and another leftover number consider as A, and then calculate, you will get the same LCM, that is the LCM of all the HCF of all the three number. Now we will see another problem, another example which is given in your textbook. Next example is 2 tank contain 504 liter and 735 liter of milk respectively. Find the maximum capacity of the container which can measure the milk either tank in exact number of times. What you have to find out? Say when you fill any tank, okay, what is the maximum number of capacity both the tank can fill, so that even if you measure number of times it should give the same value. Clear? So this tank the capacity of this is, it contains 504 liter and it contains 375 liter of milk. Find the maximum capacity of a container which can measure the milk either tank in exact same number of times. So maximum capacity you have to find out, okay, even if you measure in both you should get the same. How to find out the maximum capacity of that? So find out the HCF of this. So here the largest number is 735 and the smallest number is 504. Now how to find the HCF of this? By using Euclid's division algorithm. That is 375 equals 504. Only one time you can divide this one. Remainder will be 23. Now consider this as A, that is 504 equals 23 as B is nothing but 23, remainder is 231, you will get it. So 231 2s are you can multiply, so remainder will be 442. Now consider 231 as A and 42 as B. 40 means 4 5s are 20. So 42 into 5 you can get, and the remainder is 21. Now consider 42 as A and 21 as B. 22 2s are 42, directly remainder you will get is 0. So 21 is the HCF of those two number. So HCF of 504 and 735 is 21. Therefore the maximum capacity of the required container is the maximum capacity of the required container (21). See the another example. Next example is 3 piece of timber. Okay, we have a 3 piece of timber. The timber length is 42, 49 and 56 meter long, and it has to be divided into plank. Plank is nothing but boards of same length. Breadth should be any number, okay, or any meter, but length should be of same. All the 3 planks from the 3 piece should be same. Clear? So what is the greatest possible length of each plank you have to calculate. So what is the maximum length they can make out of this timber from all the 3 you have to calculate. Now consider what are the value they given, that is 42, 49, 56. So 56 is greater than 49 and 49 is greater than 42. Now calculate the HCF of these two. Consider 56 as A and 49 as B. So 49 into 1s you can consider. So the remainder will be 7. Now consider this as A and this as B. 49 equals 7. 7 sevens are 49. Remainder is 0. So the HCF of these two number is 56 and 49 is 7. Now this one you have to consider as A and this one you have to consider as B. Now consider 42 into 42 equals 2. 7 6 are 42. Remainder is 0. So again 7 is the HCF of that number. So HCF of 56, 49, 42 is 7. Therefore the maximum length, the greatest possible length of each plank is 7 meter. Oh, this is this much for today. So in the next video I will solve exercise 1.1 of real number of class 10. So you, wherever you are, you please open the video and watch it multiple times. You will understand it very easily, and make a note of it. Pause the video and make a note of it. Then practice it well. If you find difficulty in understanding, write it in the comment section. I will reply to that. If you like the video, please click the like button, and also if you are new to my channel, please subscribe it and click the bell button so that you will get all the notification on time which I upload. Thank you so much. Take care. Bye bye. See you in the next video.